So we'll begin our scientific program. And our first plenary speaker is Professor Tzu-Chieh from Stony University. Professor Wei's research broadly spans quantum information science and condensed matter physics. His work explores fundamental questions concerning entanglement, quantum phases of matter, and the computational and topological properties of quantum systems. The title of his talk today is Energy Space Localization, Stability Against Time-Dependent Perturbations. Please join me in welcome Professor Wei.
I hope you can hear me. I'd like to thank Professor Tzu-Chieh for inviting me to this workshop. It's great to be here, meeting new people, seeing younger faces, and other colleagues in this setting, and also a great honor to open the workshop as a first talk. So I need to find a location where maybe it's easy so I can see the slides myself. Okay, so yeah, you all heard the title, and this is joint work with my student Hongye Yu, who recently graduated and moved to Wheelchair Quantum Center at USTC. And this work, it doesn't allow me to. Maybe we should close this. Okay, yeah. So this work was recently published in Nature Communications. This is the UR code if you're interested. As just remarked, just stop me if you have any questions. So the question that we have in mind is stability against perturbation, and mostly people study static. This was hiding behind this panel here. Stability is very essential property in defining phases of matter. For example, water, ice, vapor. If you add perturbation, the solid ice still remain solid and water still remain water unless you're close to phase transitions. So there's some stability in phases of matter. And these perturbations usually considered are mostly static, time independent. And things that we know that are robust against perturbation, I list a few because I know this is a diverse audience, so maybe you catch one of these would be fine. If I don't expect you to catch everything because I don't know all the content myself, but I heard of them. So first is the topological one, like for example, in quantum Hopf system, this whole conductance associated with the topological number, chain number is robust against perturbation because it's integer. And other example including things that are protected by symmetry. For example, in S-wave superconductivity is robust against time reversal symmetry, as Anderson theorem shows. For example, it's against quench impurity. So that's why superconductivity had this VCS formula. It's quite stable. And another related example is spontaneous symmetry breaking. In superconductivity, there's also symmetry breaking. And in this particular case, there's macroscopic long-range orders such as magnetism. That's why we have them as the memory, like classical memory in our classical computers. And maybe in other area like classical system, there's integrable system, and they are stable under small non-integral perturbation. For example, in invariant tori in KM theorem, if you have non-resonant integrable system, if you add perturbation, you just perturb the orbital slightly. But if the system is resonant and you perturb, then it becomes chaotic. And in condensed matter, in the past few decades, people were really interested in many-body localization, which is basically a generalization of Anderson localization with interactions. However, this is very stable under impurities, static impurity. And its ultimate conclusion actually has been challenged. People think maybe in higher dimension than one, there's no MBL, but in one dimension, there's only one case that were proven with some reasonable assumption by Embry. And in the dynamic case, there's so-called Fouquet, that where you apply discrete Hamiltonian driven, and this can be stable against some periodic perturbation. However, in this case, you also need some of the MBL properties, so it might be limited. So I hope that some of this strike you, as you probably heard of it. And so, but most of these were time-dependent perturbation, and except this one, but it requires some static property from MBL. But time-dependent perturbation are generally much destructive, like maybe a thunder or cosmic ray hitting something. And they vary in time, so they can pump energy into the system, yeah, and break energy conservation and cause the system to jump and heat up. Yeah. So I hope you have one system that you are familiar with. Maybe let me show hand. Who have heard of topological, like quantum Hall? Symmetry breaking, right? Integral system. I was a graduate here. I remember Professor Chen Yi talk about this KM theorem in his classical mechanics class. And many-body localizations. Fouquet. Are there others that I did not list here? Maybe you can tell me, I can add it to the list. And anything that you have in mind that are stable against perturbation. Okay, so at least we agree that it is a list, may not be complete. So the question we want to ask is anything that's robust against time-dependent perturbation. So any system that has some property that we can prove is really stable against generic time-dependent perturbation. Of course, generic, I mean, there's not much constraint on the perturbation itself, except maybe you need to constrain the strains to be finite. It cannot be infinite. If it's an infinite course, it's really easily pump the heat, destroy the system. Nothing too dramatic. Well, I'll show you the condition there. And we also want to ask, are there any rigorous bounds or mathematical tool for analyzing generic time-dependent perturbation? So some example, like Lee Robinson bound, people probably have heard, and talk about a commutator of two observable. And if they are far away, it takes some time to reach, right? And during this time that the signal hasn't propagated to the other side of the location, the correlator is exponentially decaying. So but if the time is large, then there's no bound on that correlation. And these were essentially using some iterative method. You can think of it as some power series and to derive that. So it will not somehow be able to allow us to look into time that are really long. It's mostly valid for short time behavior. So the problem of time-dependent perturbation is it's uncontrollable. Yeah, and can have high excitations and heat. Okay, so what I want to tell you is some small contribution that we have is one property we call energy space localization, and that can survive under generic time-dependent perturbation. And it can then be used as a guide to search for stable phases of matter. So that's our goal. And I hope that I can convince you at the end that we achieve this goal. Okay. So I want to set up the system. So I hope it's clear now. If any question you have, just please raise your hand. And for local people like student, you can actually ask me in Mandarin. So I can also understand. For initial, we want to consider a system that is an initial eigenstate, and it's evolved under generic time-dependent Hamiltonian. Let me denote h of t. And if I start with, for example, let me pictorially, I start with h0, and I start with eigenstate, which is at E0. So this energy with respect to H0, that initial spectrum. So suppose I start with the eigenstate. We can also consider superposition of eigenstate, but it's easy just to start with one single eigenstate, and I let it evolve, right? So I can decompose this initial state, let's say psi 0, in terms of the spectrum of h of t, any instantaneous spectrum. So suppose that these solid lines are the spectrum of this h of t. So this initial dashed line will become a superposition of this. So if this is dense, so here discrete one, I would denote it as probability. If it's a continuum, and I would call it density. So, but I would just say it probability. So this state will be a superposition of these other, right, naturally. And then, but this h of t would evolve. So then this decomposition would somehow get distorted and spread out. So you would expect that the energy would quickly spread out. So, but you see, as I drew it schematically, there's some tail here. Maybe there aren't. Maybe there would also be some large peak amplitude there. But I indicated there seems to be some tail. So the question we want more specifically is, can we say anything about the tails, right? Or are they really tails? Can we prove that they are? Like, by tail, I mean the contribution will be exponentially small. Okay. Or can we, I mean, I would naively expect it might be tail, but can we prove it? Okay, so the answer is yes. So I'm going to walk you through that. I won't be able to go through every detail, but I want to get the gist of the proof. So the upshot, just tell you the conclusion in case you fall asleep. The answer is yes. So, but we have to define properly. So let me show that this is the initial state that it start with. Its energy E0 is respect to initial Hamiltonian. But I'm looking at instantaneous h of t spectrum. So I have this lambda here. Usually I'm considering it's some constant times the system size. N is the system size. So this width bounds how much energy that I could possibly input, inject, or extract. So this lambda here. So I denote it as, for example, this is the time varying Hamiltonian. This is the derivative. I take a norm, I integrate it from 0 to time. So this bounds how much energy I can pump in or extract out. Okay. So this is that. So I'm asking, let's say if we look beyond this window, like these gray area, this D is a window that's slightly bigger than this lambda. In order to look at the decay, we have to sort of look outside a little bit. As long as D is greater than lambda, this gray area has a probability that is exponential in the number of systems. Exponentially small in the number of system size. Okay, so what I'm writing here, the probability of E minus E0, let's say this is E minus E0. And I take absolute value, so I'm looking at both sides. The greater than lambda D is like this right-hand side gray area or left-hand side gray area. You add up all the probability at any instance. We're going to show that this is exponentially small in the number of system size. And this epsilon lambda is just denote this lambda here. The delta is another parameter. which is defined this way. It's 2, it's not that important, but 2 times Q. Q is the locality of the Hamiltonian, because we need to talk about special locality if we want to be able to connect to the physical system. And N is a local norm. So I would define more carefully. Local norm basically look at if you have a system of particle like spins, you look at each spin, how many Hamiltonian turn involving that turn. That roughly define you the local norm. Okay. And Q is locality of the Hamiltonian. Okay. And this exponential decaying function, we have 2 different forms. One is this exponential minus n. N is the system side. Lambda is this coefficient here. This the width we bound the energy input and output. Delta is this parameter, and there's these D is this window. Outside this window, we're looking at the contribution. D over lambda, and there's order 1 and log D over lambda. This is the standard if you have no special property. For example, some of the Hamiltonian turn, if they don't commute, then you will have this bound. If the turns are commuting, you can reduce the bound a little bit. So there's 2 types of bounds. But the most important point is this exponentially decaying in the system size. So notice that if you pick this window less than that, then it doesn't have any meaning because you would have the most contribution inside the window. So we need to ask about the contribution outside this capital D window, slightly bigger than the energy bound we input. Right? Yes, yes. So good. So we just Q local. Q local meaning that I have Q spin that can interact together. That special locality may not necessary. I could have spin here, spin there, spin here, and there. Yeah. The frequency. So this is really generic time dependent, but we need to integrate it. Yeah. You could have high frequency, but we sort of restrict that you integrated this norm. We call it a total variation of the Hamiltonian, time-dependent Hamiltonian, has to be bounded, like it's at most proportional to the system size. Yeah. Yeah. So you could have oscillation. Yeah. Yeah. Right. Yeah. 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 So because of this bound, so imagine what we usually imagine is you have any widely perturbation is okay, but eventually a long time would die down. That otherwise this integration would not converge. Yeah. You could have resonance. You could have resonance. But it's not like monotonic long time. You could have short time oscillation, but eventually it would die down because we're integrating to some time. Yeah, yeah. So as I said, it's not like generic. It's not like no constraint. There's some constraint, but it's generic enough. Yeah, that's a very good question. Yeah, you cannot like applying the cosine wave right infinitely. Yeah, it won't integrated bounded number. Yes, there's a many body Hamiltonian. It can have a long range order. Yeah. So there's no. Okay, it's very generic. So we're saying that this happens in any system, as long as the input total variation is bounded by some constant times the system size. Yeah. Yeah, this will be like order one or smaller than order one constant. Maybe it will become clearer as we go. Yeah. Yes. Yeah. So we usually we try to consider many body system. So if I only have a single Hamiltonian, single oscillator, I only n equal to 1. And this does not apply to Hamiltonian that has unbounded norm. Like a bosonic system, yeah, we'll consider mostly fermionic system and spin with finite Hilbert space. Because your harmonic oscillator has infinite norm. Yeah, yeah. So that would be somehow possible future direction that usually when people deal with the harmonic oscillator, you will truncate the photon number, for example, in quantum optics. Yes. There's no way to distinguish. Yeah, this bound does not say anything about this. Yeah, it's only saying that the contribution outside this window and large energy window, the amplitude is very small. Yeah, yeah. Maybe you will see the applications or that or implication of that. Yes. Yeah. So we would consider, for example, it's extensive. Like the energy can be extensive, but not beyond linear. Like you cannot have energy n squared, then I cannot bound that. Yeah. Yeah. You could, yes. Yeah. It does not depend on dimensionality. Yeah. Yeah, all dimension. So just give you an example. Suppose this is a real numerical plot. I have a qubit and I consider two body interaction. I have a qubit, so I could have qubit one coupled qubit two, qubit like C, A, choose two, right? Terms. So I write down generic two-body Hamiltonian, H0 and V. So they consider random two local Pauli operator. So I did not write down explicit because they are random. So for example, it could be sigma 1 with Pauli X times sigma 7 with Pauli Y, some random coefficient. Yeah. Yeah, so you can observe that this is what it's plotting is a probability in a log scale. So this is the initial, we're in eigenstate, so subtract that value. And you see that it lets system evolve. Okay, we have these lambda t, which is proportional to system size, but also proportional to t, right? T. And you can see that the energy, when it's spread, is mostly concentrated in this window. Right? This apply if this keep increasing, which is also fine, but then we won't be able to say other property like stability of phases. But this would hold, it still hold. But you see that the width is really bounded by this energy input, the bounds of energy input. So that's one example. Yeah, so this lambda of t bounds the maximum energy injection and extraction. So that's why the system mostly stay within this window, right? So you may think, well, this is actually obvious from classical physics, right? Because I only, this is the most I can input and extract the energy. Of course, my system should stay inside, right? Just like this phenomena we all see maybe in first year or second year of physics. You have a particle hitting with a barrier, well, they would exponentially decay, right? If it's classical particle, of course, you cannot have amplitude into the classically forbidden region. Right? It could also be a particle inside finite square wave. There's some decay, but mostly here. So I would say the phenomenon is analogous to this. So, but in the energy space. So that's the picture you can keep in mind comparing to that. Okay, so here is slightly more technical part. So I'm going to give some proof of this. Okay, I need to also control the time. So I may not be able to finish the talk, which is fine, but just to give you the gist, and I'll quickly show the remaining. But okay, so we need to look at energy change, right? So energy change, I basically take a wave function and then evaluate this, and I look at time variation. I look at time derivative and use Feynman-Hellman. You can just take the partial derivative, but there's only t, so really it's just a derivative with respect to the time variable here, right? And so then you integrate it. You integrated this from 0 to t, right? So the energy will be bounded by this, and I'm just taking really like generous. I'm taking the norm of the time, this Hamiltonian derivative, right? And I integrate it. So the energy difference in the absolute value will be bounded by this. And I'm going to assume that this is upper bounded by total system size times some constant lambda. That's the only assumption that I have for the Hamiltonian variation. Okay, so this can be any dimension. So there's no dimensionality constraint there. Like the example that I have, O to O, A qubit Hamiltonian, there's no dimensionality. It's right. Not bosonic, because bosonic, this thing could explode because the Hilbert space is infinite. Yeah, so we won't be able to deal with unless you make some truncation. Yeah. I don't see the Pauli exclusion play a real important. It's just a finite dimension of Hilbert space. Yeah, yeah, because we never use the exclusion in the property. Yeah. Okay, so what I do next will be I expand this in the instantaneous eigenspace. This phi is the instantaneous eigenstate of h of t, right? So, and it's very easy to see, right, that the energy probability greater than that window gray area, like gray area, is really just summing all those amplitude, right? So this is like really just a classical variable of probability. Okay. And so we're going to use something called Markov inequality. So you have some random variable, for example, this x to be non-negative, and you ask, what is the probability of this random variable that is greater than positive number a? It's actually lower bounded by the average of this variable over the number a that you gave. And you could also be using the moment, like higher moment. Okay, so we can just apply to that. So be average of this thing over dn, right? And this energy input, we want to get the average, but we can also upper bound it by the total variation lambda n. This is a loose bound, right? I'm not using because it's hard to get the exact expression of the average. So I'm using a loose bound, which is the maximum I can input. So it will be less than lambda n over dn. I'm assuming this capital lambda will be small lambda times the system size. But you could also consider the case where it's not linear, it's sublinear. That's also possible. Okay, so then you see that this is lambda over d. Yeah, it's not a very good bound, but it shows this. But if you explore that, you could also using the higher moment, and then you minimize the k so that you get a tighter bound. I'm not using a tighter bound. I'm just taking the average, but I'm using the width of the energy input and output to bound the average. So I'm getting a loose bound, but I can improve with this exponential decaying factor. Yeah. So that's the logic. Okay, if you don't get the detail, which is fine. I'm using the Markov inequality and trying to find a moment that is smallest when bounding the right on the right hand side. Okay. Yeah. The D is small d, right? Small d is the width. This is the picture. Maybe I want to keep this picture here for one more minute. This lambda here is the energy input. It bounds the energy input. It's also not a type bound because I'm taking the norm immediately. And I'm asking if the window is slightly bigger than that, D can be, yeah, larger than lambda. Smaller than lambda is meaningless. So you can consider D slightly bigger than lambda, which is fine because you have these ratio here. This, as long as you get a positive number in the exponent, then you can bound the amplitude. So this is what we call energy space localization because it's sort of localized within the classical allowed region. Yeah, just like the particle tunneling, right, into the barrier. You, if you take D infinite, then it's too loose because, of course, you're asking like very high energy. Above that would be very small contribution. Yeah, you want to, for example, in this intermediate region. Yeah, but as long as D is slightly bigger than lambda, so that the exponent is that this bracket is positive, then this will be exponentially decaying, as long as that holds. Okay. And you don't really need to worry about the difference of the two. It's just because when sometimes we can separate the total Hamiltonian into one part that are mutually commuting and another part that not commute, then this bound can be further improved. Okay. So there's a two parameter D and lambda. Lambda is the window per particle or per site, and D is the window per the energy per site that we ask outside that energy range. Okay. Measure from the initial. Maybe some system you don't have a negative energy or you just truncate it, then we'll still consider this picture. But the bound would mostly concentrate on the right hand side. Okay. Okay. The bound doesn't give you, yeah. You cannot bound things that inside because you can, within the energy window, you are supplied with proper energy that you can actually go from here to here. There's no bound on that. Okay. So in the next like 2 minutes, I'm just working through the detail of this. Okay, so basically we're considering this is subtracting the energy, right, and raised to 2K. So it's looking at the higher moment. And so this is the Markov inequality. I just include the higher moment. And I'm going to, in the end, I'm going to minimize the K. So I need to consider how I compute this G to K. And you will see that it's going to relate to a nested commutator. You need to move one operator to the left-hand side, so there will be a lot of commutator. So what I mean here, AB is the commutator of AB. And M is just applying M times of this A. Okay. So the norm, I told you we use norm, but we also define a slightly more refined norm. We label X meaning per term. So when I have a subscript X, I mean that I have a Hamiltonian, I decompose into local terms, and I take the norm of each one and then sum of that. So this, when I have an X, that's this kind of norm. But loosely, just imagine there's a norm. I bound the energy input, output. Okay, so that's this. Yeah, for the understanding, it's not that important to understand the detail of this norm. Just it's a norm. Okay, and by minimizing this k, we'll get this. Okay, so that's the procedure, and this is again the same picture. Okay, so here is the detail, but it's not that important. The logic is important. So we have this G2K, and this is actually the GK. This is actually, if you take half of this, that's this H tilde K acting on the wave function and the norm. Tilde is I subtract the reference energy. This is the initial energy I start with. So just for convenience. And because we look at the derivative as before, right? And you take the derivative inside, and you see that it's k, there are k terms. If you take derivative, you would take the derivative on the first, second, third, right? Any location of the product of k tilde, right? And therefore, I need to move. If I want to write h tilde to the left, I need to move from the left to the right, from the right to the left, right? And then that's why we get this commutator, nested commutator. So I need to move a few times, and I would have these commutator. Yeah, and then you have to bound this nested commutator. We can show that generically. There's no just the Q local Hamiltonian, because if you have commutator, like if they don't commute, two local Hamiltonian, when you do the commutator, if they have overlap, could become three local, but locality become bigger and bigger. So you need to bound the norm. So you see that there's an m factorial and there's a delta. Delta, remember we define delta as 2 times qm. Q is locality. So because you do the commutator, these terms would grow large. It's very similar to Lee-Robinson bound if you have worked through that. So we see that it's like m factorial delta m and then a single norm of this time derivative, right? When integrated, this is our lambda times n. Okay. So it's really not like this is just detail, and so therefore we can bound the derivative of this by the g and its other terms, the term before that. So there's a recursion relation, but it's inequality. It's really not important of the detail. And then you bound these G prime, G is this here, and you bound this, and so this is the important inequality we need to solve. And it turns out this is related to something called a Stirling number of first kind. And there's a function that related k to the previous k term, f terms. So we can bound this G using this F1. So the detail is not important. It's just that this can be computed. And once you compute it, and it turns out this F1 also is really just a simple product. And then we try to minimize so that we take K to be a specific number related to the D. D is the energy window we want to ask outside that. Delta is 2qm. Q, just to remind, it depends on locality Q and the system size. So you see that to bound that, the optimal bound actually need to take the moment to be proportional to the system size n. So once you've done that, everything is related to the gamma function because you see that there's some kind of factorial like. And then in the large n limit, it can write an exponential. Yeah. So that's why we get this. Yeah. So the key inequality we use here is this bounding the nested commutator. Yeah. But it can be simplified if your Hamiltonian has certain property, commuting property. When you do the commutator, the locality doesn't grow too much, then you can bound it without factorial. So we will have cases that is like that. So I don't want to go into too much detail, but essentially when your Hamiltonian can be partitioned into two parts, HC part contain those terms that mutually commute. So those terms, when they do the commutator, it won't grow the locality. But V of t would still be Q local, but there's no constraint on the commuting property. And then you have the proper local norm is less by M, and there's some also commuting property. This is the most important. This is the lambda, right? Lambda is here. M is here. The delta is 2qm. M is bounding the local norm. If you have this simplification, then the bound will be epsilon 2. Epsilon 2 will be the type 2 bound that we showed. So if it's HC is not mutually commuting, then the bound will be epsilon 1. This is just as a remark that we could have a tighter bound if the Hamiltonian has a better property. Okay. So what I talk about is dynamic energy space localization, right? If I have time dependent perturbation, I know that integrated norm is bounded. I ask the contribution outside that slightly bigger than that. The contribution we know is going to be exponential decay, right? As long as lambda is bounded, this capital lambda or as the small lambda is bounded, then we'll have exponential decay. You can also ask a slightly different question. This is the setup like this. I have a Hamiltonian H. I have some H0, some unperturbed Hamiltonian. I add some perturbation V0. I can ask if I have an energy in the total Hamiltonian, in the perturbed Hamiltonian with energy E prime. In terms of the original spectrum H0, how much does it spread? And if I know the norm, this is V0, outside this window, what is the contribution? You can ask a similar question like this. So this is like a static version of energy space localization. So that's somehow a natural question we ask. Yeah. So can we say anything about the tail? So similar to the dynamic case, we can actually say something about this. And the answer, as you now can expect from the dynamical localization, energy space localization, is that the tail will be exponentially small in the system side. Yeah. So we consider many body systems. So n is a growing number. So the conclusion is that it's going to be exponentially suppressed. So this setting is very similar to the time-dependent case. In the time-dependent case, is you have h of t is evolving, and you ask in the instantaneous energy spectrum, what is the spreading? Okay. Yeah. So actually, we have done the most hard part is the dynamic part. We can actually apply the dynamic case to derive the static case. You can consider some adiabatic evolution. But okay, before I do that, maybe I want to comment. This static energy space localization was originally also obtained in this PRL paper in Andy Lucas group. And it was also later used in the same paper used to prove infinite dynamical localization of some classical error correction code. They show that if you start with some ecstatic states, that is not the code word, but some error code word. If you have some nice property of the perturbation, then you stay inside that well, infinite long. And the leakage would be exponentially small. So I'm going to talk about that if I have time. But we want to point out that it's unknown whether the quantum version of these LDPC code I'm going to explain LDPC, what LDPC means. It's basically, low density parity check, but you will see later if I can get through that. Okay. We can directly prove the dynamical localization of quantum version, but this is just as a remark. Okay. So how do I deal with the static version? So I want this to be the initial Hamiltonian. I want to evolve to the final Hamiltonian H0, right? So that's our dynamical setting is if I have a dynamical HT, I start with eigenstate of the initial. When t is 0, sorry, when t is 0, that's H0 plus V0. That's a perturbed Hamiltonian in the set case. I want to evolve into H0. So when I set t equal to capital T, there's no perturbation. So then I can use my dynamic localization to bound the contribution of the excited states. And now the total variation of the Hamiltonian is mostly from the perturbation. So that somehow makes sense because we want to ask how much effect the perturbation give us that spread the spectrum. Then in the end, we take this t to be very small. Yeah, if you take t to be very small, your wave function will not change. So basically, you're asking this instantaneously. It's like a quench. Suddenly, you change the Hamiltonian to h from h0 to h. So sorry, the other way around. From h to h0, what is the spread? Yeah. Yeah. So essentially, that's the idea. So let me not go through that, and then you can actually show that the statement here. Outside this, you will also define a d here, d small d times lambda, and this will be small d times n. This is lambda times n. Outside that d times n window, the contribution would also be exponential decay because the proof is using the dynamical localization. Okay. So the statement, more precise statement is this: if H0, this unperturbed Hamiltonian is Q local. I don't talk about any special, right? So you don't see any dimensionality here. I only talk about locality. So if it's Q local, and the local norm is less than M, this is what we also assume in other case. And the perturbation norm, this is termwise norm, is if I know it's bounded by constant lambda times n, then initial eigenstate of this perturbed Hamiltonian with energy E prime will be spread out, but it mostly will be localized in this E prime minus dn, E prime plus dn, basically as a center of E prime to the left and or to up or to down of this with dn. In unperturbed Hamiltonian, outside the window, the leakage will be also exponential decay. It's the same bound that we have before. Yeah. And if the Hamiltonian H0 is commuting, then you can turn this into type 2 bound. Yeah. So that's why I'm saying if the Hamiltonian has a nice property, like when they're commuting, then the bound is tighter. And when they're commuting, this means that all the classical Hamiltonian is included here. Okay. Any questions so far? Yeah, locality is important because remember when we are proving the bound, we need to ask at the energy change, right? And then when we ask energy change, we take the derivative, and therefore when we want to move the underivative one to the left of derivative, we need to do the commutator. So when you do the commutator, the locality can increase, right? If they don't commute, like if you have like sigma 1, sigma 2, and then you have sigma 2, sigma 3, sigma 2 may be x of 40x, 40y. If you do the commutator, it could become 3 sites. Yeah, so therefore locality become bigger and bigger. And in fact, it grows like a power law. Like yeah. Oh, yeah, it's hiding there. So we define this delta to be 2qm. Yeah, sometimes we write the subscript q, sometimes we, yeah, yeah. Yeah, so locality is there. So, okay, so then you can ask, okay, you derive these energy space localization. Does that mean that you can somehow violate some kind of eigenstate thermalizations? In fact, actually, no, because if you look at the eigenstate thermalization, a state localized at one single energy level of a generic Hamiltonian can behave like a thermal ensemble. So it does not break ergodicity. So it does not necessary. So it may, but it might be hiding there. So localization in an energy window alone does not prevent state from being thermalized or ergodic in generic system. So in some sense, we derive a property which is very generic, like any Q local Hamiltonian with proper bounds on the perturbations or time dynamics. You have these energy space localization, but somehow we don't get anything beyond yet, right? Yeah, so let me just skip this. Yeah, so energy space localization, we understand it can survive under generic time dependent, but does it give us something new, right? Maybe that's it, right? Like just like particle decay and that's it. And can we use it to get some other stability beyond the energy space? So that's the next, I don't know how much time do I have? 5 to 10 minutes. Okay. Yeah. So this is thing that I use AI for. So we feed our paper to AI and ask AI to generate like a summary plot of one. So if I don't think I can finish, but at least I can show this AI picture. So there's some slightly tweaked by human. So this is the initial state. You see that it's, and if you there are some instantaneous eigenspectron here. If you evolve in this spectrum, it can spread out. So somehow AI were able to capture the essential point. And things that we can use this energy space localization to get some new stability is as this. For example, we can prove that for certain error correction code with some nice property, it is actually a good thing. It's a shield for qubit against errors. So the local parity check. So I might not have time to explain what that is. So it's showing the stability. If something hit that, it's stable. So there's a shield for errors. The other application actually is somehow from one point of view is bad is because you have such localization, it's actually is a trap for quantum algorithm. So quantum algorithm, if you use time-dependent adiabatic or something using time-dependent Hamiltonian-driven, you won't be able to get out of these well. So that's somehow it's a bad thing. Okay. So given that I have 5 to 10 minutes, so let me explain the idea. So to search something stable, a stable phase, using energy space localization, just talking about energy itself is not enough. You have to relate this localization to other property like configuration, the spin configurations, and therefore you can say something new about that. So for example, in many body localization, you need to know these configurations. There's some L-bit property of that. For example, spin glass model, this classical model, and also error correction code could be classical or quantum. There's some nice property about these. There's energy and also configuration space. They have these like nice landscape. So you have configuration that are somehow separated by some energy spacing, and energy barrier, and has some these could be some local minimum, and they're separated by some distance. This is the distance in the configuration space. Like it could be comparing how many flip you have in the so-called Hemingway distance. Yeah, so their low energy eigenspace is well separate into we call clusters. And these within each cluster, they contain configuration, these up down, they're close enough. And so configuration or eigenstate require some energy in order to overcome the barrier to reach other clusters. So adding this property and the energy space localization, then we can prove that if you stay inside each cluster, it will stay under generic high dynamics with the proper norm of these Hamiltonian variation. Then the state will stay inside as well, exponentially long. So that's the result we showed. So this applied to spin glass that had these kind of landscape, and also applied to error correction code where the lowest energy will be 0. So that's meaning that there's no error, but there's some linear relation with the energy and the configuration distance. Yeah. So I don't have time to talk about this, but there is an insight from Garmanek and Sudan that proposed the so-called overlap gap property to explain why some problems are hard. So we all know there's some NP-hard problem, random K-set, maximum independence set, etc., P-spins. They propose something called energy overlap gap property. So essentially, what that means is that for various solutions, they're either close or they're and they're all far away. So this R basically is the overlap. So the overlap between two solutions is from -1 to R1 or from R2 to 1. So they're either very far or very close. So there's nothing in between. So they call this overlap gap property. You could also define in terms of Hamming distance. This term somehow is generated by AI. AI said that this is a Hamming desert. So the picture is like this. So if you require, for example, you want to do some optimization problems, and you require that the ratio to the n, if I require this ratio to be very low, this bound, let's say this is like 0.1, I want the optimization problem. Usually, they consider maybe it could be optimized to a maximum. If the ratio is small, then any solution is valid, right? If the ratio is like close to 1, then to get optimal solution will be very difficult. So this is the picture. So if the causal quality value alpha, if it's very small, then every configuration, they sort of in single connected component. But if you start with increasing these alpha, then the valid solution become clusters. So there are small regions that are with close distance that are solutions. So they become clustered. So this is the picture. They either very close or very far. It's called Hamming desert. Okay. So why is that important? Because then we can sort of relate the energy and eigenstate with this defining this clustering property. So let me define this, and then I'll state maybe conclusions. So if the Hamiltonian has the clustering property between E1 and E2, so this is as this picture shows, the solution or eigenstates in this energy range fall into two cases. If they are in the same cluster, then the distance is within nu1, and if they're in different cluster, there is some distance between them. So this somehow looks like an energy barrier. There's some trap here. In order to get to this cluster, you cannot directly tunnel. You have to go through the excited states, higher excited state, and then come down. So it looks as a barrier. For example, a new one generally is slightly small, and new two need to be sufficiently large in order for you to get a good property. The separation in the error correction code will be the code distance. But I don't think I have time to talk about that in detail. Yeah, so let me just show. I don't have time to explain the error correction code. But maybe let me just say what is LDPC. As a local low density parity check. So you have qubit or bit, and these are checks. Check you can write as poly Z's or poly X. LDPC means that you look at any vertex, the vertex degree need to be of order 1. So this is showing the shows 9 qubit code. If you scale with system size, 9 qubit, for example, become n square qubit, then you have this large number of degree. So Shor's code is not LDPC. But toric code is LDPC. If you have heard of toric code, you know that it defined on torus, and the Hamiltonian defined on these checks, these 4x or 4z. It's a LDPC code. So because the maximum degree is 4, but it only encodes 2 logical qubits, so not a really good one. Okay. Okay, so let me just state our result. So our results show that if the code exhibits some linear energy barrier, the error induced by weak time-dependent perturbation will remain correctable if the total variation is small. So basically, that's a picture. If this is the configuration or landscape of error correction code, these are the ground state with 0 energy. This is the code word. And this could be an excited state, meaning that there's some error. If the total variation of the Hamiltonian in terms of perturbation or dynamics is small, then this excited state that has error will stay within the well exponentially long. If it stays within the well exponentially long, you can measure its property and then bring back and correct it back to the code word. So that's the essential idea. Yeah. So maybe let me go to the conclusions. Oops. Okay. Yeah, so we give a bound in energy space spreading that works for generic Q local Hamiltonian. The application is shown in these 2 diagrams generated by AI. It has non-trivial consequence on system with linear energy barrier. So it can be spin glass, could be NV-hard problems, as long as they have these linear energy barrier, like in some LDPC code, they would exhibit extreme stability. So they would be exponentially long staying inside each cluster or well or cohort. If it's classical LDPC code, one could actually prove that it's stay infinite long. But of course, there's some leakage. The leakage would also be exponentially small. But since a sharp knife have two edges, so the other edge that's bad is for optimization problems that are hard, we want to use quantum computer to solve. But if we use the Hamiltonian-driven one as an algorithm, the system can get trapped and would not be able to find the global minimum. And for potential experimental tests, because we might need to have long-range interaction, so maybe a trapped ion can be served as a platform that we can test these LTPC co-stability, and therefore proving the energy space localization. Okay, so that's it. Thank you very much for your attention.
So thank Professor Wei for the inspiring talk. So now it's open for a few questions.
Why is it important to use the example of low density parity trap codes, or if another codes will work in the same way? Which lies in not in this category?
Okay, that's a very good question. So we want these linear energy barrier, right? In some spin glass problem, it has been proved these overlap gap property. From that, we can show these clustering property. But only recently that people have proved the LDPC code has that property. Yeah. But if you can, it doesn't need to be LDPC, but if you can construct code that has the property. But we want LDPC because we want the delta Q, which is 2Q times M, we want the locality, right? We also bound a local node. If the code is like really large, has large Hamming weight, like Shor's code extended to like n squared qubit, you will have of order n weight of the stabilizer. And then we cannot bound Q. Q is not a constant. Q will be proportional to system size, which is not good. Yeah, thank you.
Any other question?
Yeah.
Original Leaf Robinson bound is the bound for velocity of a spin chain where propagate.
Yeah.
And in this case, so in what sense where the Leaf Robinson bound in energy space?
No, it's not related to Leaf Robinson bound. The only connection to that is like we all use these commutator, nested commutator.
Okay.
But Leaf Robinson bound has these exponential like distance minus velocity times t.
Yeah.
That only holds right when t is small.
Where
T is smaller than distance.
Case where
Yeah.
where energy difference is the probability with a higher energy difference is given by
Exponentially small.
Right? And so for small t, where it's proportional to lambda, and so lambda is given by the typical, I think, the highest frequency of the Hamiltonian.
So, lambda bounds the norm of the Hamiltonian change.
So does that lambda gives a kind of velocity sense of Leaf Robinson?
Not, I think it's a different.
I see.
I don't think they're related.
Okay. And if you say this as a energy space localization, but and eventually where pumping of energy is saturated by the lambda, the system size. but if the system size is very large, then you can pump as much
You can
yeah,
pump, you can absorb energy that's proportional to the system
to
size.
the yeah.
If it's too large, then we won't be able to bounce.
So then can you
Yeah.
estimate the typical time for protecting some state or
Yeah.
you wait for a longer time, then I think that state will be become unstable.
Yeah. So we can show the time, how long it can sustain, like exponentially.
Okay.
There's an exponent that we can show. Yeah. But there are also some system that's infinite long. So it can be stable infinite long.
Yeah.
But for those exponential dynamical localization, we have an estimate of how large it can go exponentially. Yeah. Yeah. That's a very good question. I sort of skip over the detail.
Thank you very much.
Thank you.
Okay, so I think we can stop here. So that thank Professor Wei once again.
Thank you very much.